All right, so we're going to continue the discussion on waves and oscillations today. And what I want to talk about this time is what happens if you have multiple waves going through a certain space at the same time. So for instance, let's say we have one wave like this moving along, and then we have another wave. Maybe it's got a different amplitude or same amplitude, maybe it's got a different frequency. And they're both moving, and let's say they're both at the same place, so they're on top of each other. I just drew them separate just to make it clear that it's two different waves. So you have these two waves flowing through space at the same time. What happens? Do they interact with each other, or do they not interact with each other? Well, in general, they will interact with each other. And the good news is, if you want to know what happens when you have multiple waves all at the same point at the same time, is that you could use the superposition principle. Now, this principle comes up in a lot of different areas of physics, and it sounds fancy. All it means is, if you have multiple phenomena occurring at the same time, and you want to know what is the total result of all of these phenomena all occurring at the same time, then all you have to do is take each one individually, add up the results of each one, combine them all together, and the final sum of all of those results is the actual total result. So for instance, if I have two waves moving in the same point at the same time, then all I have to do is add each wave together. I'll get a new wave, and that new wave is what is the result of the two waves acting at the same time. So if these two waves like I've drawn actually happens, then really all I have to do is take one of the waves and the other wave. Each one has a value, so let's say the value at x equals 1, and x equals 2, and x equals 3. I would take the value of our new wave, call it, let's say, y, is going to be the value of the first wave at some x, plus the value of the second wave at that x. Okay, so that's the value of the total wave at x. And then if I want to know the value at the next point in space, then I just take the value of the first wave at this new point plus the value of the other wave. So you're just adding each wave together to get a new amplitude for our final wave. This results in what's called interference. So, waves will interfere with each other. There's two types of interference. There's constructive and destructive. And the difference basically is, constructive interference is when you have your two waves, when you add them together, they're both in the same direction. So for instance, let's take constructive. I'll have a wave like this. Okay, and let's say I have another wave, and he looks like this. Then, if we look at these points, let's say this point here. Notice the blue is on the positive side, and the black at the same point, at the same x position, is also on the positive side. So, when we go to add them, you'll be adding two positive things together. It gets bigger. That's constructive interference. However, if we look over here at this point, point 2, at this point here, notice the black is positive at that point, but the blue is negative. That means when you go to add those 2 points on the wave together, some is going to be positive, some is going to be negative. They subtract from each other. That's destructive interference. So what's going to happen when you add 2 waves together, you're going to get points that may be bigger than either of the other 2 waves, or you'll get points that's smaller than either of the other 2 waves. Constructive interference is when they add together and both positive or both negative. Destructive is when one is positive and one is negative, and so they reduce each other. Now, with that knowledge, we can ask a question something like this. Let's say we have these 2 waves, a wave that looks like this, and we have another wave that's its exact opposite. So anytime the black is positive, the blue is exactly the same value but negative, and vice versa. When the black goes negative, the blue goes positive, and they're both of the same amplitude. This is total destructive interference. What winds up happening is, let's say the value of the wave right here, maybe the black point is at +2 and the blue point is at -2. So when I add those two, y at this point x is y1 at this point x plus y2 at this point x. Well, I get y1 at that point x is +2, and y2 at that point x is -2, and so I get a value of 0. And if we have total destructive interference, then any point x you choose when you're adding these 2 waves together, you're always going to get 0. So the actual value when these 2 waves interfere is purely 0. You get nothing. So this is interesting. You can have 2 real waves. Let's say these are water waves, or maybe they're sound waves. You're sending these waves out. When they combine, they cancel each other out perfectly, and you get no wave coming out. So if this is, for instance, sound waves, maybe these are 2 trumpets playing, and if it happens that these 2 trumpets play waves that are exact opposites like this, then someone listening to the 2 trumpets actually don't hear anything at all. Their sounds completely interfere with each other destructively, and you hear complete silence. And this actually happens. This is one of the big worries when people are designing amphitheaters and auditoriums and things where maybe music's going to be played, or concerts, or even speech or something like that. You have to be very careful about how you design the room and how the sound waves reflect off the walls and get to certain points in the room, because it might be that when someone plays their trumpet, when the trumpet wave reflects off of the left side wall and it reflects off the right side wall, when those 2 waves come together later on, they may destructively interfere. And so someone sitting in a particular seat in this room may hear nothing. They don't even hear the trumpet playing, even though the trumpet is playing. But then someone next to them, where the waves don't completely interfere, would hear the trumpet play. So this is a very, very big problem when designing auditoriums and things like this, to design the rooms in such a way as to minimize this effect. Now, sometimes you like this effect. For instance, things like sound canceling headphones. They like this effect. And so what a sound canceling headphone will do is it will have a little microphone built into the headphones and listen to all the sounds coming in, and then it'll play the exact opposite sounds into your ear, so that when your ear hears the original sounds coming in, plus what the headphones are feeding into your ear as well, which are the opposites, those 2 sounds cancel each other out and everything becomes silent. It's this exact destructive interference that allows this to happen. So what we want to do as a calculation type thing is, can we predict when sound will interfere with each other destructively or constructively? So we want to do some calculations on interference. Now the big equation we're going to have for interference goes like this. If you have two sounds, so here's a source here and here's a source here, and they're playing their sounds, and maybe we have a microphone over here listening. If the sound wave traveling from this side and the sound wave traveling from this side, when they reach our microphone, they're going to interfere with each other. Are they going to interfere destructively or constructively? And the way you figure it out is the difference, or the change, the difference in path length, so how far this left side wave has to travel, minus how far this right side wave has to travel. If they constructively interfere, then this path length difference must be some multiple of the wavelength of the sound itself. So, basically this means if the wave traveling from the left and the wave traveling from the right, when they reach some certain point, if they happen to have waved exactly the same amount, so that this guy is at this point coming from the left, and this guy from the right is also at that point going the other way, then notice they're both at the same point. When they add together, they give the same number. So this equation basically says these two waves will interfere constructively if, completely destructively, constructively, if the difference in path length between the two different waves is some multiple, that's what this n means, some multiple of the wavelength. So n could be 0, 1, 2, 3, any number you want, as long as it's an integer. And if we want completely destructive interference, then it's n lambda over 2. This is destructive. Okay, so thankfully the two different equations are fairly easy. They're pretty much the same. If we have destructive interference, and that's the kind of case where you've got the wave moving to the right like that, the wave moving to the left when it reaches this point here, let's say, then this wave, the blue wave, is on the upswing while the black wave is on the downswing. That means they're half a wavelength apart. When one is going up, the other one's going down. They're 1/2 wavelength apart from each other. Then when we add those two waves together, they destructively interfere and they cancel themselves out. So if the path length difference is a multiple of the wavelength, they add together. If they're a half multiple of the wavelength, then they destructively interfere and they cancel each other out. So let's try an example, just to make it clear how this works. So there's a speaker is placed at the origin. A second speaker is placed 10 meters to the right. If the speakers play a sound of 114 hertz where should you place a microphone to get constructive interference? So the little drawing looks something like this. Here's one speaker. Here's another speaker. And we're going to say, where should I put the microphone? Let's say I put the microphone right here. Well, what do I know? I know the distance from this speaker to this speaker, that's 10 meters. So when you're asked where should you place a microphone, generally that means, how far from the origin? 2 meters away, 3 meters away, where should it be? So we'll let the distance from the origin, or from the first speaker to where I expect my microphone to be, I'll call that X. And that's what I want to find. What is this distance X? Now that also means the distance from the microphone to the other speaker, that distance must be 10 minus X. Because say the microphone's at 2. If the microphone is at 2 from the left, then that means from the microphone to the other speaker, well, it needs to go all the way to 10. It's at 2, so it needs to go another 8 meters. So 10 minus this 2 is 8. That's where this equation comes from. And we've seen this in Physics 1 as well, with certain example problems. You know the distance relative to one speaker, and then you take the other distance relative to that distance. And so that's 10 minus x. And now if we're going to do constructive interference, our equation is the difference in distance, the difference in the path length from the left speaker to the right speaker, must be some multiple of the wavelength, if this is constructive. So in order to do this, first thing I need to know is what is the wavelength of the sound for this particular problem. Well, I know the frequency of the sound is 114 hertz. And I know the equation V, the velocity of a wave, is the frequency times the wavelength. So this will tell me the wavelength of this sound is the velocity of the wave over the frequency. And I happen to remember the velocity of sound is 343. That's just something you should remember, and I'll probably give it on a test. But you should remember sound's velocity is 343. The frequency is 114. So we stick this in our calculator, and we get the wavelength is 3.008 meters. So now I know the wavelength of the sound. What about this path length difference? Well, what's the difference in the distance from the speaker to the microphone on the left and a speaker and a microphone on the right? Well, I know the distance from the speaker to the microphone on the left, that's x. That's what this distance is right here. And so the difference in path lengths is that x minus, now we need the other guy's distance. Well, I already know his distance as 10 minus x. So this is the path length difference. The sound coming from the left speaker goes a distance x. The sound from the right speaker goes a distance of 10 minus x. The difference between those, you just subtract them. What does that equal? That equals some n, where we just leave it as n for now, times whatever the wavelength is for this problem, which is 3.008. And now all we have to do is solve this for x. X will tell me where I should put this microphone. So we clean this up a little bit. We have x minus 10 minus minus x, so that's 2x. Remember, this minus with that minus makes it a plus, so x plus x. Then we have minus 10, that's the left side, equals n times 3.008. Now again, I want to solve this for x. I'm going to bring the 10 over. So I get 2x equals n times 3.008 plus 10. And I want x by itself, so I divide by 2. I get x is equal to n times 3.008 plus 10 over 2. And that's the answer. Basically, if I want to know where I should put this microphone, first thing this tells me is because there's the n sitting there, and I could choose what value for n, then there's multiple places I could put this microphone and still get constructive interference. There's not just one place, but there's many places. What are those places specifically? Start plugging in values for n. Remember, n has to be an integer. So for instance, if we let n equals 0, what do we get? We get the value of 0 times 3.008, that's just 0, plus 10 divided by 2, 10 divided by 2 is 5. So if we place the microphone at the 5 meter mark, we'll get constructive interference. But we can also choose n is equal to 1. If we choose n is equal to 1, then we have 1 times 3.008, that's 3.008 plus 10, 13.008 divided by 2, that gives me a value of 6.50. So that's another answer. I could place the microphone at this point. Or, again, I could choose n is equal to 2. Choosing n is equal to 2 gives me 8.008. And so on. Not only that, I could also choose n is equal to minus 1. Because you could have negative integers as well. If n is equal to minus 1, then I have minus 3.008 plus 10 divided by 2, that's 3.5. And so on. Now, in general, what you would want to do given a question like this, you would give every value that's between 0 and 10. So for instance, if I try to do n is equal to 3, would I still get an answer? Yeah, I would get 9.5. But then, if I try to do n is equal to 4, 4 times 3.008 plus 10 over 2, now all of a sudden I have 11. Well, 11 is to the right of this speaker, and I just want to know in between the speakers. Now, for our problems, for the problems on my kind of a test or something like that, you could give me this as the answer with the n in it. And that's the main answer. Or if I say, give me the values for n is equal from 0 to 2. So then you'd get me, these answers here. The actual values. But just be careful, if you're in another class or another professor, they may ask you to give every single value that's obtainable. So you'd have to do all the different n's. Now, of course, we could extend the example. We could do destructive interference. If you wanted to do destructive interference, you do exactly the same thing, only now your equation is delta L is n lambda over 2. And you go through exactly the same work, and you'll get different answers for this. So that's how this is going to work. Be on the lookout. I'll be posting some practice problems on this stuff. But as you can see, it's not too complicated. As long as you know the distances involved, then you just plug them into this simple equation. You may need to calculate the wavelength if it's not given to you in the problem. Calculate it out, plug it into the problem, and then solve for your main answer. And then if you want specific numbers, that's when you start plugging in values of n. N being an integer, a 0, 1, 2, 3, or -1, -2, -3, whatever values you want. And that'll give you the actual places. All right, hope this is helpful.